Hello everyone. In this video, we're going to be talking about a way to multiply two vectors together called the dot product. So if I have two vectors, v equals v1, v2, and w equals w1, w2, the dot product between these vectors is denoted by v dot w. And as we denote the dot product and write it using symbols, this explicit dot between the two vectors is a mandatory part of the notation. Later in the class, we're going to be talking about another way of multiplying two vectors together called the cross product. So we need to be really careful in our notation to make sure that it's clear which of those two products we're talking about. So when we're talking about the dot product, that is symbolized using a big dot between v and w. If you want to calculate the dot product between these two vectors, here is the formula. I have a vector v dotted with a vector w, and the formula is take the first entry of v, take the x component of v, and multiply it by the x component of w. Then add the y component of v and multiply that by the y component of w. So x component times x component plus y component times y component. This is the dot product of these two vectors. If you have a pair of three-dimensional vectors, the formula extends in the expected way. If your vectors are three-dimensional, you would just multiply the z components together and then add that into the result as well. So let's get some quick practice using this formula to calculate some dot products between two vectors. For example, here I'm asked to calculate the dot product between the vector 2, 4 and the vector -4, 6. So I'll take the x component of the first vector, 2, and I'll multiply it by the x component of the second vector, -4. And then I'll combine that with the y component of the first vector, +4, times the y component of the second vector, +6. So now evaluating that using PEMDAS, I have -8 from the first product and I have 24 from the second product. So I get from this dot product the number 16. And I emphasize that the result of this dot product calculation is a number, is a scalar. When you multiply a pair of vectors via the dot product, the result is a scalar. Part B, let's practice dotting together a pair of three-dimensional vectors. So the first vector being 5, -1, 3. The second vector being 6, 2, -4. To calculate this dot product, I would multiply together the two x components, 5 times 6, and then I would add in the product of the y components, -1 times 2, and then I would add in the product of the two z components, 3 times -4, and then I would add all those results together. So that's 30 -2 -12. That is, again, 16. That's an incredible accident of these two problems I have created. So once again, and I really cannot emphasize this enough, when you dot together two vectors, the result is a scalar. One of the most common errors that I see from students working on this section is multiplying the two vectors together and turning the final answer into a vector as well. And if you make that mistake, it'll really mess you up in a lot of future lessons. I will say that of all the topics that we study in this class, in my opinion, the dot product is the one that is the most useful and the one that is used over and over and over again as you progress into future STEM classes. The dot product is used quite a bit in future math classes, including Calculus 4, and especially in linear algebra. Linear algebra uses like a million dot products. Later in this class, we will be using dot product several times. Dot product is also used in contexts like physics, engineering. I have also seen it used even, for example, in computer algorithms. If you've ever been to Amazon or Netflix and they have recommended you products or movies that they think that you will enjoy, that algorithm used to recommend products to you actually utilizes a dot product. So this is a very, very important quantity in terms of how useful it is. And so if you cannot calculate this quantity correctly, it can cause you a lot of trouble in the future. So please bear this in mind. When you calculate the dot product between two vectors, the result is always a scalar, a number. And we're going to talk today about what that number means and what it's telling you about the two vectors, v and w. Other notable properties of the dot product. First of all, the dot product does not care the order in which you multiply the vectors together. If you multiply with v first and then w, or if you multiply with w first and then v, it doesn't matter. You're going to get the same result in either order. The order of that product does not affect the result. The second property of the dot product is that it actually is related to a vector's length. Specifically, if you dot a vector with itself, the result is equal to the length of that vector squared. And that just comes from the fact that if you do v dotted with itself, that's equal to v1 times v1 plus v2 times v2. And so that's equivalent to v1 squared plus v2 squared. And that's the same thing as the squared length of v. Now let's explore what the dot product means and what it tells you about the vectors v and w, specifically how those vectors are graphically related. To that end, let's go ahead and do some experiments and some exploration. We're going to be given a couple of different pairs of vectors v and w. We're going to graph those vectors on the xy plane, and then we're going to calculate the dot product between the two vectors. And from those experiments, we'll deduce one of the things that the dot product is used to tell us. Here we have the vectors v equals 3, 1, and w equals minus 4, 1. So if I sketch in the vector v, the vector v is pointing into the first quadrant, and if I sketch in the vector w is pointing into the second quadrant. Now let's calculate the dot product between these vectors. V dotted with w is equal to 3 times negative 4 plus 1 times positive 1. So that's negative 12 plus 1. So that's negative 11. So our dot product has produced a negative value in this situation. Let's change things up. Let's change our v vector to 1, comma 1, and let's change our w vector to 3, comma 2. If I now graph these two vectors, v equals 1, comma 1, and w equals 3, comma 2, I can see that the vectors are both pointing into the first quadrant. So these vectors are pretty closely aligned, actually, close to pointing in exactly the same direction. Now, if I calculate the dot product between these two vectors, I get a result 1 times 3 plus 1 times 2. So that's the result. 3 plus 2 equals positive 5. Positive 5. So in this case, our dot product has produced a positive value. Finally, in part C, we have the vector 2, comma 4, and the other vector negative 4, comma 2. So let's go ahead and plot those vectors on the xy plane. I'm going to try and draw this quite carefully. V points 2 units in the positive x direction and 4 units up. W points 4 units in the negative x direction and 2 units up. So what I want to note is that these two vectors in this example are actually perpendicular to each other. So let's go ahead and calculate the dot product between the vectors in this situation. V dot W here would be 2 times negative 4 plus 4 times positive 2. So that's negative 8 plus positive 8, result 0. So in this situation, where the vectors were perpendicular to each other, then in that instance, our dot product produced a value of exactly 0. So let's take stock. In the first example, our V and our W were mostly opposed to each other. The angle between the vectors was quite large, so the vectors v and w pointed, roughly speaking, in opposing directions. In the second example, our vectors were pointing in almost the same direction. The vectors were mostly aligned. In other words, these vectors had quite a small angle between them. And in this final example, we saw that the vectors are perpendicular. In the case that the vectors were mostly opposed, the dot product produced a negative value. In the case that the vectors were mostly aligned, the dot product produced a positive value. And in the case that the vectors were perfectly perpendicular, the dot product produced a 0 value. So the conclusion that we can draw from these experiments is that the sign of the dot product tells you whether the vectors are mostly aligned, mostly opposed, or perpendicular. Specifically, to reiterate what we said above, if the dot product is producing a positive value, then this is a sign that V and W point in roughly the same direction. Perhaps not exactly in the same direction, but they are more aligned than they are opposed. If the dot product returns a negative value, then this is an indication that V and W point in roughly opposite directions. They may not be pointing in exact opposite directions, but they are more opposed than they are aligned. And if the dot product is equal to exactly 0, what we say is that the two vectors are perpendicular, or you might also hear the language orthogonal. Orthogonal. Basically just a fancy term for perpendicular. But this is a piece of terminology that we will have on our language test, orthogonal, because it is a piece of terminology that is so common in the field. Orthogonal means that the dot product between the two vectors is 0, which graphically is an indication that they are at a right angle. So this is the significance of the sign of the dot product. This is the significance of, is your dot product positive, negative, or 0? So then it's a question of, okay, what is the significance of the magnitude of the dot product? What does it mean if the dot product has a large magnitude, like 11, versus if the dot product has a small magnitude, like 1 or 2 or 3? To explore what's going on with the dot product's magnitude, I've prepared a little GeoGebra module here so that we can see the dot product of two vectors in various cases. So here on GeoGebra, I have two vectors v and w, and I can adjust those vectors by dragging around their terminal points. And up here I have some text which is calculating and displaying the value of the dot product between the v and w that are currently drawn. So right now my v and my w are drawn both pointing into quadrant 2, and they're more aligned than they are opposed. They're pointing in roughly the same direction. The angle between them is relatively small. And so corresponding to that, we're getting a dot product that's equal to a positive value of 4.91. As I adjust the vector w to point in an opposing direction to v, what we see is that dot product becoming negative as those two vectors begin to separate from each other. So now the vector v and w are separated by a very large angle, and so that's showing up as a negative dot product. So that's a verification of what we found earlier. So now let's see what happens as we take the vectors v and w and adjust their length. If I make the vector w longer, what I see is that the magnitude of that dot product grows. And as I make the vector w shorter, the magnitude of the dot product gets smaller. Similarly for v, if I make the vector v long, then the value of the dot product grows in magnitude. If I make the vector v short, then the dot product shrinks in magnitude. So we can see that the value of the dot product is going to be affected by the length of v and the length of w. It's going to be affected by that, and it's also going to be affected by the angle between the vectors. If the vectors are close to being perpendicular, you see a dot product that's very, very close to 0. Because if the vectors are perpendicular, if the vectors are orthogonal, then the dot product is equal to 0. So if the angle between them is close to 90 degrees, that also causes the magnitude of the dot product to go down dramatically. And then as the angle between the vectors shrinks towards 0, the magnitude of the dot product increases. So the magnitude of the dot product is affected both by the length of v and w and by the angle between the vectors v and w. So the specific relationship between the dot product, the length of v, the length of w, and the angle between them is given by the following equation. V dot w is equal to the length of the vector v times the length of the vector w times cosine of the angle between the vectors, which I will denote via the angle alpha. So v dot w is affected by these three quantities. If the length of v is big, that will make the dot product bigger. If the length of w is big, that will make the dot product bigger. And if the angle between the vectors is either 0 or 180 degrees, such that cosine produces +1 or -1, that will also make the dot product big. As opposed to if the angle between them is 90 degrees, cosine of 90 degrees giving you 0, and that will make the dot product small. Now, this equation can actually be used to calculate the angle between two vectors, both in two-dimensional space and in three-dimensional space. So let's go ahead and practice using that formula to find the angle between the vectors v equals 6 comma -1 and w equals 2 comma 3. To that end, I'm going to need to take this expression and calculate the dot product, the length of v, and the length of w, so that the only unknown left in this equation is the angle alpha that I'm trying to find. So calculating v dot w, I get the number 6 times 2 plus -1 times 3. So that gives me a result of 12 minus 3 equals 9. So a positive dot product indicating that these vectors are more aligned than they are opposed. So I should expect the angle between them to be relatively small, less than 90 degrees. The magnitude of the vector v is equal to the square root of 6 squared plus -1 squared, which, if we want to simplify that, becomes the square root of 37. And the magnitude of w is equal to the square root of 2 squared plus 3 squared, which returns a value of 13, if I've got that correct. So let's plug that information into the equation v dot w equals the length of v times the length of w times cosine of the angle between those vectors. If I then want to calculate the angle, I can do that by dividing the equation by the two lengths, and then using inverse cosine and applying that to that fraction to generate the angle alpha. Now let's go ahead and graph these two vectors and check see if this value of alpha makes sense for the vectors in this picture. Okay, here we are with the vector v being 6 comma -1 and the vector w being 2 comma +3. And we can see indeed that the dot product between those vectors is +9. And that +9 is reflecting the fact that the angle between these vectors is relatively small, less than 90 degrees, an acute angle. And in the picture we see that the angle separating v and w, this angle right here, does look to be around 60 degrees. So our answer makes sense for the vectors in this picture. That concludes this video on the dot product. We learned how to calculate the dot product between two vectors. It's denoted by v dot w, and the formula is take the x components and multiply them together, take the y components, multiply them together, take the z components if you have them, multiply those together, and then add those products together. Because you're adding those products together, the result of the dot product is always a scalar value. And what does that scalar tell you? Well, first of all, the sign of the dot product tells you whether your vectors are mostly opposed or mostly aligned. If the sign of your dot product is negative, then your vectors point mostly in opposite directions. If your dot product is positive, then your vectors point mostly in the same direction. And if your dot product is equal to 0, then your vectors are at a right angle to each other. They are perpendicular, or what we call orthogonal. That's the significance of the sign of the dot product. The size of the dot product is affected by several factors. The size of the dot product is affected by the length of the first vector, the length of the second vector, and cosine of the angle between the two vectors. And you can use this formula to actually calculate the angle between two vectors by solving this equation for alpha using inverse cosine.